Well, g'day flatties and globe defenders. This is Critical Think from Down Under. Thank you very much. As I have previously mentioned, I've been to Thailand a little bit this year and I've taken some weight measurements as I've been travelling around, and I'm going to present them to you in this video. And also, I'm going to answer this question. How do I know the Earth is not flat? Now, by the time you get to the end of this video, the answer will be obvious to everybody, that is, except flat earthers, I assume. Now, here's a sunset in Thailand, and you can see, obvious to anyone except flat earthers, that the sun is shining on the bottom of the clouds. The colour of the sun, the shadows, the time of day. Yes, sir, that is one piece of evidence that confirms globe. But that's not what we're talking about today. Today we're talking about weight change versus latitude. Compelling evidence which confirms beyond reasonable doubt that we live on a rotating spheroid. Now I'm going to play again a clip that I've played before. In my opinion, it never gets old. It will only get old when the author of this clip retracts his incorrect statements.
Goes on about the difference in the weight of things at the equator compared to other places in the Earth. Have you actually gone and measured it? Have you ever done it? We understand that in the model, based on the spin and centrifugals, centripetal whatever forces, that's the result that you can calculate based on your model.
And we do.
But has anyone actually gone and measured this so-called difference? Has anyone actually measured that a kilogram weighed in somewhere up north is any different to a kilogram weighed on the equator?
Exactly.
Has anyone actually gone and done that? No, they have not. A kilogram is a kilogram wherever you are on the Earth.
So let's talk about this. And you know, from my previous videos, I've done this measurement, this experiment. So here we are again. Why is this my favorite experiment? Not many people realize this is a real measurable thing. It's a non-optical observation, and then therefore there's no optical drop and limited angle excuses, and no flat earth explanation for the naturally observed phenomenon. This is observable, testable, repeatable. It's a falsifiable hypothesis, and anyone can do the experiment. Statistical analysis eliminates flat Earth as a valid hypothesis. Flat earthers have a lot of trouble coming to grips with that because they don't understand maths or statistics or anything like that. And this does demonstrate the existence of a rotating spheroidal planet, and it's real-world evidence of the gravitational equation. We use the equation to predict the weights, and the measurements confirm the prediction. Through my experimentation and analysis, I figure I am a subject matter expert on this topic. I don't think anyone else has gone and measured like this as much as I have, but maybe they have, but I don't know about it. So what have been the flat earth cult objections? Well, we've had straight up denial, which is something that you heard in that video clip. And I know David Weiss has also denied that this actually can be measured. There's arguments about, it's the air density, the air temperature, the air pressure, or magnetic field. Well, those effects are very minimal, and I'll demonstrate through the statistical analysis that's all of those things. I have before demonstrated that there's no correlation between the weight and those things, and so they're just random effects that are not going to randomly put your weight into the exact reading that matches the globe model. No, random variations in density, air temperature, air pressure, and magnetic field are not going to do that. They're going to produce random results, not a correlated result. And Rachie has said, there could be variations in gravity. Okay, so you're admitting gravity exists now. And there's people have said, oh, yes, that's very good, but I think you need to repeat the experiment. Well, I've done it a lot of times already. It's been repeated and repeated ad nauseum. And some people have said, oh, you don't have a dependent or independent variable. That's obviously false as well. And another flat earther, oh, my jeweler says, oh, blah, 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 blah. So your jeweler's a physics expert now. That's a bit like asking your hairdresser what's wrong with your car. And you go to the mechanic and you say, oh, my hairdresser says this is wrong with the car. And the mechanic's going to look at you very strange and go, huh? What, really? So I've even been told that, because there's no mainstream media mention of this, then he hasn't heard of it in the mainstream media, then it's not real. And how can some random dude on the internet, that's me, have any credibility when, no other scientist is whatever or TV channel or whatever has mentioned it? Like I said, well, maybe it is that I'm breaking new ground here and I am now perhaps the subject matter expert on this experiment. And again, I have to ask, well, what happened to do your own research? Is that gone by the by now? Oh dear, oh dear. And I will debate anybody on this topic. Bring it on. A neutral platform for debate, that is. Not one of those platforms where the mute button is overused. So I'm going to go back again over the theory. I've been over it before, but here's a reasonably quick recap. So the two forces that cause the weight of an object. There's the gravitational force, which of course is in the downward direction, perpendicular to the surface. And that gives an acceleration of 9.8 meters per second per second. Then there's this other component. And yes, you can't feel it. You can't feel it. It's small. And it's this here I said is Fy, which is the y component of my centrifugal force, which is perpendicular to the axis of rotation. So the y component is the component perpendicular to the surface. And that's why we've got this cos theta here. Now at the equator, the amount of force gives an acceleration of 0.034 meters per second. And so you can see that it's way, way smaller than the gravitational force. And you often hear floodies, oh, we're spinning at the breakneck speed of 1,000 miles per hour. Why don't we just fly off? Well, this is why you don't fly off. You do the numbers, you do the calculation. Look at that. That's a minuscule. Fly-off force is minuscule and heavily outweighed by the gravitational pull towards the center of the Earth. So these two forces, we can predict what anything should weigh anywhere on the Earth to within a small percentage. I mean, there's going to be variations. It's not going to be perfect. So you'll see that the gravitational force gets smaller as the R gets bigger. So at the equator, where the Earth is a little bit fatter, the gravitational force will be a little bit less because of that. And also the centrifugal force gets greater as you get further away from the center of the Earth. So there's two things there to make something lighter at the equator. It also means that as you go up a mountain, for example, this will change because your R is different now and your weight will get lighter as well. Another thing to note is that Fy will get smaller as you move away from the equator. So the latitude increases, cos theta gets smaller, the radius of rotation gets a lot smaller, and so this centrifugal component will become less and less. At the same time, the gravitational component will become a little bit larger because the R will decrease slightly because of the oblate shape of the Earth. So the net effect is as you move away from the equator, the weight will increase. So here I've worked an example. So if I were to take 1,000 grams of weight and weigh it on an accurate scale at the equator, and then go to 30 degrees latitude without recalibrating the scale, then it should weigh 1001.31 grams. Now that is a very small change. So you can see, if you want to measure this, you're going to need an accurate and stable scale. Now, in this case, a 0.1 gram accuracy should be good enough. Now, I'm using a scale that says its smallest increment is 0.01 gram, but its declared accuracy is 0.1. Actually, the scale, its accuracy is around 0.03. So some scales won't take 1,000 grams, they'll only take 500 grams. In this case, I still think that a 0.1 accuracy should be good enough to get some meaningful results. So what equipment did I use? Well, I've got this reliable scale now, the Digitech electronic scale. I haven't recalibrated this for quite a while. I wanted to take a few measurements with the same calibration just to prove a point, and it's maintained its calibration pretty good over these 12 months or so, maybe a little bit less, that I've been using it without recalibrating it, and that's very, very good. Now, I can't say the same for this scale on the left, this yellow coloured one. A very nice looking scale, but it sort of drifted out of calibration very quickly, so it wasn't a big help. So I used exclusively this Digitech scale, and also I'd done a few measurements here and there with this scale. The problem with this scale is that you cannot level it. You have to find a level surface, and that's pretty critical in getting accurate measurements, but it will do the job. You know, if you want to do on the cheap and you don't want to carry around a bulky scale, a scale like this one, now there are others in the cheap range, but I found this one that looks like this is performing fairly well for me and gives a fairly consistent result. So this is the scale. You can buy it under a number of brand names, but they all look like this with the name here, the brand name in there. It may or may not have a brand name, but they'll just put their own brand name. The OEM manufactures this, sells it to a lot of people marketing the same scale. And I'm assuming it's all the same scale no matter the brand. So how we go about improving the accuracy? We use a reliable scale with a stable calibration. I only measure indoors. I've tried measuring outdoors, and big problems with trying to level the scales and wind. And I do take several readings at a particular location just to make sure I get a stable reading. Critical here, important, make sure the scales are level. You'll see why in this video. And then I record the weight, the latitude, and the elevation. So let's look at the measurements. So here in the northern hemisphere are the locations. I've got Singapore, Phuket, then a few readings in Bangkok, and then up through the Asan area in the northeast of Thailand. In the southern hemisphere, I've got readings at Redcliffe and Brisbane and Sydney. Now the results. I've graphed them all up. All my readings are there from late December 2021 to July 2022. And when I plotted them, the blue line is the readings. The orange line there is the prediction. There's a pretty close match. We'll go into the significance of this in a little bit. Here's my standardized and normalized plot, which I've eliminated height as an independent variable, and just so to see how it follows the curve for just the WGS 84 latitude at one particular height. So this one here, calibration weight, I've put as 900, and then most of these readings are on the green line, which is the WGS84 model. Now this one here is odd men out. I had a look at that. Oh, what's happened there? That doesn't look right because I get such good results. Here, this one is an outlier. So I looked again at the picture I took with the scale. So here I am in the Qantas lounge at Sydney International, and I think I was just too much in a hurry or distracted or something, but I missed out one of the vital steps of making the scales level. And look at that, the bubble is right off there to one side, and that's going to ruin my reading. And it did. So here's another reading I did in Sydney, different location, another date, and the bubble's a little bit more centered this time. From this angle, it looks a little bit off center, but it's probably bang on when you get over the top. So they're different reading in the same city because I didn't have the scales leveled. Now, in a previous video, I gave all my results, which is from Wolfie did some measurements, Mr. Thrive and Survive, and others, and this is the plot that I had then. So I've added my measurements to the totals, and here most of my measurements are down this area and up around here. There's my Sydney measurement. Here's Bob's measurement that was an outlier in his case, and you can see they're all clustered around the WGS84 model. So good evidence for the globe, but how good, we'll get to check that in a little bit. So when we do the analysis on this, we've come up with, there's 87 data points, and the WGS84 model explains 98.7% of the variation. Now, doing the same analysis for the flat Earth model does not explain it at all. 0% correlation with the flat Earth model. Let's just assume now that the Earth is flat, and we'll have a look at the hypothesis of the Earth being flat. Now, if we were to go out and various locations and take weight measurements, we would expect something in the order of this, because we're looking at effects of density changes, temperature changes, maybe magnetic or whatever you like. There'll be some variation due to these things, but the variations are small. So you'd expect on a flat Earth, you'd get something like the green dots. Now we actually get measured with a scale the blue dots. So you got to ask yourself, well, what are the chances are that the Earth is still flat, but we made an error in our measurement? And this is where the statistical analysis comes in. For the data, I've calculated a variance, what I've called a variance, which is a bit like a standard deviation, but slightly different. Standard deviation is calculated on the average of the samples. And in this case, it's more appropriate to apply the standard deviation as the difference between the predicted and measured values, and that's what I've done here. The standard deviation of the residuals is a little bit less than that, so I've taken my variance, a bigger value, which helps the flat Earth. And so in this case, if I were to take a measurement, and it should be in this range, sort of like there where the green dots are, and I actually measured it down here where the blue dots are, if the Earth was flat, and that's a mistake, this can happen, but the chances of that, because that's 8 sigma away, chances of that is 1 chance in 100 million. There's a lot of zeros there behind that. Now that's if I do it once. If I do it many times, the zeros you can just add, keep adding. So the chance that the Earth is actually flat is in this particular, just this one reading, is 1 chance in 200, and there's a bunch of zeros over that. a bunch of zeros after that. And if you were to take all these readings in conjunction, there'd be so many zeros you couldn't count them. So that's how I know the Earth is not flat, because I've done these measurements, and the chances are so infinitesimally small that this was a mistake, that the Earth is really flat and I've just measured wrong. The chances are infinitesimally small. So really, pretty much impossible that the Earth is flat. So, thank you for watching. Please like, subscribe, and share this video. Thank you.